Hi, this is Andrea Hendricks, and let's take a look at Section 2.1 Homework Problems. I've selected some problems from the textbook exercises, but again, these should give you a feel for what you need to do online. There are a lot of concepts in this section dealing with being able to read graphs, so we're going to go through a lot of those problems, and contact me if you have any questions after this. We want to first determine the intervals of the domain over which each function is continuous. That word continuous really means that you can draw the graph without picking up your pencil. And so if you look at number 12, if we placed our pencil on number 12 and drew the graph, notice that we could go through the whole graph without moving our pencil, so that is continuous everywhere. So the entire domain is what we would answer. The entire domain is, since it extends indefinitely to the left and to the right, that would be that it is continuous on the interval from negative infinity to infinity. Number 13 is also continuous on its whole domain. The problem is its whole domain is not the whole real numbers. It starts at 0 from the leftmost point to infinity. So remember, domain is your x values. Okay, so remember, we're really superimposing those down to the x-axis to see what x values are covered. Number 15, we cannot draw the entire graph without picking up our pencil. We would have to move it around this value of negative 3. And so it's continuous everywhere else. So we would say from negative infinity to negative 3, using a parentheses to exclude that, and then from negative 3 to infinity. Same thing happens with number 16. There's a hole in this graph, so we would have to pick up our pencil to draw it. Where does the hole occur? It occurs at the x value of 1. So it is continuous from negative infinity to 1 with a parentheses union 1 to infinity. Now the next concept about reading graphs dealt with determining where the functions were increasing, decreasing, and constant. So increasing means that the graph is going up from left to right. Decreasing, the graph is going down, and constant means the graph is horizontal. That is, the y values are constant. The y values are not changing. Now again, we answer with intervals of the domain. So part A says to find where the graph is increasing. Well, the graph is increasing where we go up when we move our pencil, and that happens on this particular piece here. But what x value does that begin at? That is at 4. So for part A, we would answer at 4 to infinity. We include the endpoint if the point is included on the graph. Part B, where is it decreasing? Well, it's decreasing on this piece over here, right? As we move from left to right, we're coming down. That is all the values to the left of negative 1. So that is from negative infinity to negative 1 with a bracket. Now, where is it constant? It is constant in this region right here, but I'm answering with the x values. Those x values are from negative 1 to 4. Now, give the domain for part D. The domain is the graph continues everywhere from left to right. The domain is negative infinity to infinity. Part E is what is the range? Well, remember the range is bottom up, the y values. Well, the bottommost y value occurs here, which is at the y value of 3, and then the graph extends upward. So we would say the range is from 3 to infinity. Number 19 is almost identical to this, except that the graph is going to change where it's increasing and decreasing. In part A, where is the graph increasing? Well, that's increasing here from negative infinity up to the x value of 1. Where is it decreasing? That's decreasing here, which is the x value of 4 to infinity. Okay, remember I'm talking about the x values. The x values are to the right of 4. Now the y values are certainly getting smaller. They're going to negative infinity, but I'm answering for the x. Where is it constant? It's constant here. That is between the x values of 1 and 4. Now my domain, from left to right, everything is covered in the x value. So that's from negative infinity to infinity. And lastly, the range. Range is from bottom up. So that is from negative infinity to the highest y value, which is 3 with a bracket. We can do one more here. Where is it increasing, decreasing, constant? So let's see, increasing is here. What x value is that? 3. Now the difference here is we don't put a bracket on 3 because that endpoint is not included here. Where is it decreasing? Let me do a different color here. It is decreasing from this portion of the graph, which is from negative infinity up to what x value? That's negative 3, but again, it's not included, so we have a parentheses. Where is it constant? It's constant here. So we would say from negative 3 to 3 with a bracket. Now the domain is going to be a little bit trickier here. So we go from left to right. Notice that there is a whole inner graph at this value of negative 3. So that negative 3 is excluded from the domain. Now here there's a gap and a hole at the value of 3. But notice one endpoint includes 3, the other does not, but 3 is included in the points at least one time. So it's still in the domain. So even though it's not continuous there, it is continuous as far as how we write the domain. So we would say from negative infinity to negative 3 with the parentheses because of this hole, union negative 3 to infinity. Because it picks back up here, and then it looks like it's stopping, but it's already included and continues on to the right. Now the range, the bottommost point is where? The bottommost y value is at 1. And notice it goes on up indefinitely because these points between 1 and 3 are included for this portion, and then on up is included. So it would be from 1. Oops, do I put a parentheses or a bracket though? Yeah, 1's got an open circle there, so I have to do a parentheses to infinity. Now, the next few problems says to graph the function in the standard viewing window and trace from left to right along the portion of the specified interval, then fill in the blank with either increasing or decreasing. So I have drawn here the graph of number 32, and I have it done two ways, even though it said to do in the standard viewing window. On my second way, I've changed it, and I'll talk about that. But on the standard viewing window, if I put in x squared minus 2x and graph in the standard viewing window, what I want to find out is if I go from the x value of 1 to infinity, is the graph increasing or decreasing there? Well, here's my x value of 1. And if I go on the portion of the graph to the right of 1, notice I am increasing on that interval. Well, you can actually enter the restriction that you're looking at in the calculator. If you only want to view the graph from 1 to infinity, what you can do is input the function and then do a division symbol and then type in the restriction on x. So I'm only looking at values which are larger than or equal to 1. And I have to do this in parentheses. Remember, I can get the inequality symbol by doing the second and math. And so I'm typing in that x is greater than or equal to 1, which is what that 1 to infinity means. And then it only graphs for me that piece on this portion of the domain. And there I can see that that piece is increasing. You definitely don't have to go to all of that trouble, but just another way to look at it. Now, these problems are to use visual observation to determine whether each graph is symmetric with respect to the x-axis, y-axis, or origin. So symmetry is really like that mirror image that we were talking about. So you're thinking of, could I fold the graph along the x-axis, y-axis, or origin and still see a similar shape? So in number 37, if I fold the graph along the x-axis, so fold it in half, and I wish I could show you this really good, but do you notice how that would be a mirror image of itself? So this is symmetric with respect to the x-axis. Now if I folded it along the y-axis, there's no portion over here, so I wouldn't have a mirror image. Number 38, well, the origin, origin is if you fold it on the x-axis and y-axis together, would you see a mirror image? And that would not be true in that case because it's not symmetric with respect to the y-axis. Okay, so here with the origin, so that is if I fold it, or you can even think about folding it along through the origin. It's harder to do. But what I suggest is thinking about folding it over the x. If you folded it over the x, you would get this piece here. Then if you folded that over, you would get this piece here, so they would coincide with each other. And so number 38 is symmetric with respect to the origin. Oops. Okay. I'm messing up these graphs, so whenever you print this, it won't look good, so let me erase that there. Okay. Now, let's look at number 41. Is it symmetric with respect to the x-axis, y-axis, or origin? Well, the x-axis would mean if you folded it down, notice what you would see. You would see this piece down here and this piece up here, which are not mirror images of each other. So this would not be symmetric with respect to the x-axis. The y-axis would mean that if you fold this piece over here, you're going to see this piece and this piece. A lot of times it's good to draw these on a piece of paper and actually fold it along the axis so you can see if you see the same picture when you look through. And that's not symmetric with respect to the y-axis. Now the origin would mean, let me erase that here. If I fold it along the x to get this piece, and then fold it along the y, I'm going to get this piece here. So this one is symmetric with respect to the origin. Okay. Now, number 42, is it symmetric with respect to the x-axis, y-axis, or origin? Well, x-axis, hopefully you can see that's not, because if you fold it along the x, you would have this here. But if you fold it along the y, notice that those pieces are going to lie on top of each other. If I fold this piece over, that's going to lie on top of this. So this one is symmetric with respect to the y-axis. Now, complete the table if f is an even function. Okay. Even function means that f of negative x is equal to f of x. Other way you can say it, it's symmetric with respect to the y-axis. Also, we can say that opposite x have equal y values. So the way you could do this is this. If I know that negative 321 is on the graph, opposite x values would have equal y values. So the y value at positive 3 would have to be the same as the y value at negative 3. If I know that 2, negative 12 is on the table or on the graph of f, then opposite x would have to have equal y. So that would have to be negative 12 there. For negative 1, negative 25, opposite x have to have the same y value, or the equal y value. So that's how you complete the table, knowing that information. Now what if the table is odd, or the graph is an odd function? Odd means f of negative x is equal to the opposite of f of x, or opposite x have opposite y values. And this one is symmetric with respect to the origin. So if I know that negative 513 is on my table, opposite x have opposite y. So that would tell me this y value needs to be a negative 13. If 3, negative 1 is here, opposite x have to have opposite y. So if this is negative 1 for positive 3, it has to be positive 1 at negative 3. At negative 2, negative 5, opposite x have to have opposite y. So that would be a positive 5. And then for it to be an odd function, it always has to go through the origin. So we know that has to be at 0, 0. Now we can complete the right half of this table, or this graph, if we know the following things. I'm not going to do both of these. Let's just do one of them. Let's do part A, says if the function is odd. If the function is odd, that means that opposite x have opposite y. So for instance, if I know that this point is negative 1, 1, and this point is negative 2, 0, this point, let's say, is negative 3, negative 1. When I'm drawing the odd part of it, I would have to do opposite x have opposite y. So negative 1, 1 would become 1, negative 1. Negative 2, 0 would become 2, 0. Negative 3, negative 1 would become 3, 1. So the graph would look like this. Now this was to use the graphing calculator tables to determine if the function is even or odd, so really kind of practicing that. So what you're looking at is this: how do the y values compare for opposite values of x? So when the x values are opposite, what is true about the y values? At 1 and negative 1, the y values are opposite, right? At 2 and negative 2, my y values are opposite. At 3 and negative 3, my y values are opposite. So since opposite x have opposite y values, this means that this function is an odd function. Prove analytically that each function is even. So to prove it's even, I have to determine if when I plug in negative x, do I get the original function back? So let's look at number 51, for instance. So what I'm going to do is plug in negative x everywhere I see an x and see how my function is changed, if at all. So if I raise a negative to the 6th power, a negative to an even power is positive. So this is just going to become x to the 6th. Minus 4 times, if I raise a negative to an even power, I still get just x to the 4th plus 5. Well, notice that is my original function, right? That is f of x. So f of negative x is equal to f of x, so that proved that that function is even. Prove analytically that each function is odd. Well, like in number 58, what I'd have to do is plug in negative x. So if I plug in negative x where I see the x, this one you have to think, negative to an odd power is negative, so that would be a negative x cubed. Negative 4 times negative x would be plus 4x. Well, notice how every sign from my original function is changed. In other words, if I factor out a negative 1, I get negative times x cubed minus 4x, which is the opposite of my original function f. So since f of negative x is the opposite of f of x, this proves that this function is odd. Now it says to use the analytic method to determine whether the graph of the given function is symmetric with respect to the y-axis, origin, or neither, and then use your calculator to support it. Well, symmetric with respect to the y-axis means that it is an even function. With respect to the origin is an odd function. So what you would just need to do here is plug in. Let's look at number 65. If I have f of x is equal to x cubed minus x plus 3, when I plug in negative x in place of x in that original function, let's see what happens. Well, negative to the third power is negative, so that's really negative x cubed. Negative times negative would be plus x plus 3. Well, look at the signs from my original function to my new function. The first sign is the opposite. The second sign is the opposite, but notice the third sign is plus. It did not change. So this is not the same thing as the opposite of the original, nor is it the original function. So this one would be neither even nor odd. Or you can say neither symmetric with respect to the y-axis or origin. But here's another clue. Notice that my power on 3, or the first term is a 3. The power on x is a 1. What's the power on 3? Well, do you know that that's really an understood x to the 0 power? And anytime you have a combination of even and odd powers in your function, it's going to be neither even nor odd. But you still should be able to support that analytically. And then graphically, you could graph this function, and I'll show you how to do that on the calculator part, and see that it doesn't match the symmetries or the table that we've talked about. Okay, so that concludes this material. If you have any questions, don't hesitate to contact me. Thank you.